Hello, and welcome to our presentation on CWE 656, Reliance on Security through Obscurity. In this presentation, we're going to discuss an overview of the CWE, a real-world example, demonstration of our code, and mitigation strategies to avoid such flaws. So let's start with a high-level understanding of CWE 656. So CWE 656, called Reliance on Security through Obscurity, is a weakness where systems rely on hiding details like passwords or protocols to stay secure. The problem is that once attackers uncover these hidden details, the system becomes completely vulnerable. So why is this a problem? The main flaw is that hiding details is not a strong security strategy. Attackers can reverse engineer systems, analyze memory, or intercept network traffic to find what's hidden. For example, if a program stores sensitive data, like passwords in its code, an attacker can easily find and use that information to bypass security. So where does this happen? CWE 656 commonly shows up in, number 1, embedded systems. So developers assume that attackers can't reverse engineer their proprietary protocols, but tools like debuggers make it possible. Number 2, web applications. So obfuscating JavaScript or hiding API endpoints might stop casual users, but skilled attackers can inspect code or network traffic. And lastly, the last example we're going to go over is configuration files. Hard-coded secrets like API keys or database credentials are easy to extract if not protected. So how do we go about fixing this? To secure the systems, the first thing we want to do is avoid relying on hidden mechanisms or hard-coded secrets. Use encryption and secure access controls to protect sensitive data. Assume attackers will see the system and design it to remain secure if it is exposed. So CWE 656 reminds us that real security doesn't come from hiding details. It comes from using strong, tested methods that stand up even when details are known.
Here in blog post 2, we're looking at CVE 2024-5244, a real-world example that highlights the risks of relying on security through obscurity. This vulnerability affects TP-Link Omada ER605 routers, which are business-grade routers used to manage network traffic. The flaw lies in the CMX DDNSD executable, part of the COMEX DDNS service, which allows remote access to a network by linking a domain name to a changing IP address. Attackers exploit the service to impersonate hosts, overflow buffers, and bypass ASLR, a security feature that randomizes memory locations to make attacks harder. In short, this flaw allows attackers to gain root access to the system, proving that hiding mechanisms alone doesn't make a system secure. So what does this mean, and what can we do about it? Once attackers gain root access, they can monitor network traffic, steal sensitive data, and use the router to compromise the entire network. To prevent this, here's what needs to be done. Disable the COMEX DDNS service if you don't need it. Update the firmware regularly to stay protected. Segment the network to isolate critical systems. Monitor traffic for any unusual activity. Enforce strong access controls to limit unauthorized access. The key takeaway here is that security through obscurity fails instead. Design systems assuming attackers can see everything and ensure they remain secure even if exposed.
A common theme among security through obscurity vulnerabilities is the assumptions being made by the developer. The assumptions can be many and varied, however generally concerns the fact that attackers do not have direct access to the source or to the hard-coded secrets. Our vulnerable program is a basic password checking program. It compares a user inputted password against a hard-coded password using string compare. The assumption made by the developers is that the attacker would not be able to gain access to the source code or to any of the secrets contained in the binary executable. Attackers can exploit this by running the strings command with the executable as input. They get text strings contained inside. Afterwards, attackers have access to the secret and will be successfully granted access by the program when they use it. So we will first start off by compiling the exploit. From there, we can simply just run the exploit. And as you can see, we find the password and we have been given access. So in conclusion, CWE 656 is a security flaw with real-world examples that is easily fixable through proper assumptions during the design and development of a system.